All right, we're doing a hard one today. Find the median from a data stream. This is problem 295. So the median is basically given a list of numbers. You want to return the median. And it's one thing to note, it is an ordered list. If the size of the list is even, there's no middle value. So the median is the mean of both of those middle values. So for this example, 2, 3, 4, the median is 3 because it's in the middle. And for this example, 2, 3, it's an even list. So you will add 2 plus 3 and divide by 2, equaling 2.5. So you'll be returning a double. And you want to implement the median finder class. So you have an object, you have a function that adds the number from the data stream to the data structure, and then a find median. And you can go down here, you see the constraints that we're going to be going pretty high, and we'll be doing a lot of calls. So we want to be efficient in terms of how we're solving this. That's basically what these type of things are hinting at you. It's saying, hey, we're going to be doing a lot of transactions. You need to make this space and time efficient. So if we're trying to run a real-time median calculator, some of the things we can think about, like how we're going to get this done, is what data structure are we going to use? So one idea that comes to mind, which is probably how I'm going to solve this, is heaps. So basically, if you have an ordered list and you want to find the middle elements, I think the best way to store that ordered list is to divide it into two lists and then keep adding onto the tops of those lists. So whenever you want to get the middle element, you can compare, like, is this 5 and is this 5? If so, then it's an even list. It's 10. So pop off the 2 off the left side and the right side, add those together and divide by 2. And if the left side is bigger than the right side, then you know it's an odd list and you can just pop off that element. So we're going to use heaps because that's the data structure that pretty much solves this problem. So a heap, min heap, let's do max heap first. So a max heap will be the left side of the ordered list. And this will store the smaller half of numbers. And so because we're storing the smaller half of numbers, that's why we're doing a max heap, because we want to get the biggest element off of that because that's closest to the middle. And then for the other side, for the min heap, the min heap will store the bigger half of elements, like over here. So if you want to conceptualize this, right? Let's say we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 as our input. Max heap, smaller half of numbers. 1, 2, 3, 4, 5. Min heap, bigger half, 6, 7, 8, 9, 10. And when you poll, you will get 6 because it's the minimum. And here, when you poll, you'll get 5 because it's the maximum. So in this example, it's 10 elements, it's even. So you would just poll 5 and poll 6 off. So you get poll min heap plus poll max heap divided by 2 equals 5 plus 6 divided by 2. And so that's your answer, 515. And if it was different, if it was say 1, 2, 3, 4, 5, 6, 7, you'd have 1, 2, 3, 4, and then 5, 6, 7. And here you can compare the length, since the left side is going to get added to first and then added to the right. you can say, okay, this is greater than the length of this, so we know it's odd. So just poll left side equals 4. And that is the answer. So let's implement it. First, create the priority queues. Then instantiate them in the constructor. Now, by default, priority queues are min heaps. So when we do a max heap, we're going to have to do a custom comparator. So it's just a lambda function. And we're saying we want to do b minus a, which says greatest, like a max heap. So big on top. And then do the right min heap. And these are default min heap, custom comparator for max heap. Okay. Now let's get into the logic of adding a number. So we're always gonna insert into the left. Okay. Then we're gonna balance it. So basically, we put the number in the min heap. It's always gonna go in there first. And then as we keep adding numbers, or the max heap. So it's always gonna be on there. And so when we pop off that max value, it'll automatically balance and move the biggest value onto the other side for the right min heap. So we can easily balance between. So it's kind of just popping off and bouncing over there, if you can conceptualize that. So rebalance though, you're going to get confused here. You're like, well, isn't that just going to keep adding? Yes, but we're going to rebalance it. If the right heap is bigger than the left heap. Oh, let me add that. Didn't even do it. So right here, we're moving the biggest element from the left side to the right side so we can keep it even. We don't want to have one skewed. So if left max heap dot size is less than right min heap dot size, then left max heap so right here, if the left max heap size is less than the right min heap size, then that means the right half has more on it. So we're going to add to the left side over here, we're going to add to the left side the smallest element of the right side, thus ensuring balance. Just make sure our syntax is correct. Okay, now for the finding the median, if left max heap dot size is greater than right min heap dot size, return left max heap dot peak. Else return left max heap dot peak. And here we're going to be adding them. And we're going to divide by 2.0 to get that double. If you divide by 2, you'll truncate the integer values, and you run into some problems. Boom. Did not beat a lot of the complexity here, but in my opinion, doing a priority queue for this is so readable, so easy to manage. For space complexity, we did pretty good. And this would be log n for space complexity, because each insertion and rebalancing operation takes log n due to the heap. And then finding median would just be O of 1. Our space would be O of n. So I will upload a commented GitHub link here so you can check that out. But yeah, you got to get familiar with utilizing queues, min heaps, max heaps, and manipulating them in order to pass these problems. But good luck. That was a good hard.